Okay, let's get started. This is CS161 Discussion 8 walkthrough, and we're going to be talking about web security today. So we're going to pick off where we left off last time. So now we're exploring a few more concepts around web security. So let's start with the same origin policy. So what is the same origin policy, or SOP? Well, the premise of this is that we don't want websites to be able to modify data on other websites. And so if we're on google.com, we don't want Google to be able to modify data that's on facebook.com. And so the way that browsers protect against this is that they use the SOP to determine which sites are from the same origin. So how does this work? Well, the origin consists of these three components of every URL: the protocol, the hostname, and the port. So the protocol is this HTTP : // Another one that you might see is HTTPS. These are two different protocols. Hostname is the second component of this. So hostname is this actual domain. So in this case, example.com. And port is the port number that is attached to the end of the domain. And if you don't see a port number, there's still a port there. It's just whatever default port is specified. So one key thing to note here is that we don't really care about the path. So anytime you're on a website where these three criteria match, that is what consists of the origin. And so we don't really look at the path when we're talking about origin. So this is an example of comparing websites that have the same origin and ones that don't have the same origin. So walking through these really quickly, you can see in this first case, the initial components of these, so the hostname, the port, the protocol, all of these things are the same, and the only thing that differs is the path here at the end. And so these are the same origin. For the rest of these, there's usually something that's different. In this first case, we have a different domain here, so a different hostname. We have www.wikipedia.org and wikipedia.org here. So because those are two different host names, these are not the same origin. In the third case, we have HTTP versus HTTPS. So this makes it so that those are different origins. And in the fourth case, we have two ports that are explicitly different. So in these three cases, none of these sites are considered to be the same origin. Now, one key thing to note here is that websites with different origins may communicate through a narrow API that is controlled by the browser, and that is this post message API. So there's a few exceptions to the same origin policy. So in general, the origin is defined by the URL of the website that you're accessing, but the exceptions are JavaScript and images have the origin of the page that loads them. So if you're running JavaScript inside of a page, it's going to run with the origin of that page. And the second exception is that frames have the origin of the frame source. So if you have some iframe that looks like this embedded on a website, this frame is going to run with the origin of google.com because that is the source of that iframe. All right, now let's talk about cookies and session management. So cookies, what are cookies? Well, cookies let us save information within a browser, and the browser is the ultimate manager of the cookies, and so the browser is what determines cookie policy. So what makes up a cookie? What are some components? Well, we have 5 components here, and let's just walk through these. So the domain of a cookie is whatever domain that cookie was saved under. So in this case, example.com. We might also have a path, which is specifically what path was that cookie saved under. And we have a few other attributes here. The secure attribute is a Boolean, and if it's true, then this cookie will only be sent over HTTPS connections. So in this case, if we are potentially setting a cookie value that we want to protect, and we don't want an eavesdropper to be able to see, we ensure that it only is sent over the network when the connection is secure. this flag here, this HTTP only flag, says that we don't want this cookie to be modified or accessed by JavaScript. And so any scripts that are running on that page, if the HTTP only flag is set, they will not be able to access or modify that cookie. And finally, the expires flag is an integer value where the integer itself is represented in epoch time. So it is time in, I believe it's either seconds or milliseconds since 1970. And so this is typically a really big number, and usually what happens is if this time is in the past, so for example, if the time value is set to -1, then the browser will look at that cookie and essentially delete it because it will be expired. And so one way that your server says, hey, I want to clear cookies in the browser is it sends back a value of -1 for this expires flag, and that'll tell the browser to delete that cookie. But typically, we can take the current date in epoch time and add, maybe 2 weeks, convert it into seconds to this number, and set that as our expires flag. And in that case, this cookie will expire in 2 weeks. So that is cookies. And cookie policy is essentially what lets us dictate when to send these cookies and when to allow servers to set these cookies. So there's 2 different parts to cookie policy. The first part talks about when cookies can be set. So if a web server wants to set a cookie for a browser, so say you're logging into Gmail, the Gmail web server may want to set a cookie for your browser so that every time you load Gmail and interact with Gmail, that cookie is saved in your browser and interacts with whatever requests you make. And so what determines which servers can set cookies for which websites is cookie policy. This is part 1 of cookie policy. So 2 rules apply when a server is trying to set a cookie. The first is that the cookie's domain must be a suffix of the server's URL. And so if we have some web server, eeks.berkeley.edu, and it's trying to set a cookie with the domain of eeks.berkeley.edu, that'll work fine. If it's trying to set a cookie for the domain of berkeley.edu, that'll work fine as well. So essentially, if you have a really, really deep recursive website, so cs161.eeks.berkeley.edu, that site can set cookies for anything all the way up to this parent berkeley.edu site. Now, how far does this go? This goes all the way to the top level domain. So eeks.berkeley.edu cannot set a cookie for the .edu, but it can set anything, any cookie values for the berkeley.edu or eeks.berkeley.edu sites. So that's number 1. Number 2 is that the cookie's path can be anything. So if you visit eeks.berkeley.edu/home, that can set a cookie for /home. That can also set a cookie for /about. And so this is important to note when you're designing sites where you might have variable paths. So that is the second important note. Now let's talk about part 2 of the cookie policy, which is when cookies are sent. So if you're sending cookies to a web server, so in other words, if your browser is making a request to a web server, we need to figure out, hey, which cookies should we attach? So we have some, cookie jar here, and our browser is going to look down in our cookie jar and say, hey, which cookies should I attach? I'm making a request to this web server, and the cookie jar will give it back cookies based on this policy. So there's really one big component. The cookie domain must be a domain suffix of the URL domain, and the URL path must begin with the cookie path. And so if these criteria are met, the cookie will be sent along in the request that is made to the server. And so that is cookie policy part 2. Now let's look at an application of cookies. And this application is concerned around session management. So what is session management and why is it useful? Well, let's first look at this analogy here. So session management is like wristbands. When you go to a concert or an event or something like that, maybe the first time you present a ticket or your ID to a ticket guy, and the ticket guy gives you a wristband back. Now you put that wristband on, and every other time you enter this concert, maybe throughout the same day, you just show the wristband. And maybe when you leave the concert, he cuts off your wristband and he says, this is now expired. So session management is effectively the same policy. So we have a browser and a server, and maybe at the beginning of this interaction, when we haven't really done anything, the browser says, hey, here's my username and password to the web server. And at that point, the web server will say, okay, let me give you a wristband so that in future times you can send the wristband. So the web server will generate this random number, and we call that a session token. And it's going to save that session token along with your username after it's validated that, hey, this is actually a valid username and password. It's going to save the session token and the username in this table. And this table we call the sessions table. Now, after that, it's going to respond, and it's going to set the cookie, the session token cookie, to ABCD. And at this point, your browser will have a cookie with the session token value of whatever the server gave you. So in this case, the server gave back ABCD. And so this is going to be saved in a cookie. And so the next time we make connections to this web server, say we want to load emails. The session token will be sent across because it's a cookie that matches with the cookie policy. And the web server will say, okay, I have this session token, but who does it correspond to? Whose wristband is this? So it's going to go look up in its table of session tokens. It's going to find the username, and then it's going to perform whatever action it needs to perform with that username. And then it can return data back. So why is this better than just sending across a username and password each time? Well, the first time we send a username and password, we want to effectively throw away that username and password in future interactions with this browser so that the browser doesn't have to keep hanging on to this password. And so the session token is one way in which we can ensure that the browser doesn't have to hang on to this password in future interactions and only has this session token value instead. Now, session hijacking is one attack on session tokens where if an attacker gains access to a user's session token, the attacker can use it to access an account. And so this is why we usually make our session tokens really, really big numbers, really big random strings effectively, and we want these to have enough randomness so that an attacker cannot just brute force guess session tokens and get into accounts. So these are some FAQs about session tokens and cookies. The first thing to note is that session tokens and cookies are two different things. Session tokens are effectively one potential value that a cookie may have. So session tokens are stored as cookies, but cookies can have other values as well. So maybe you have a cookie for the time that you establish the connection or something like that. And the second one is, what is the difference between the same origin policy and cookie policy? Well, remember how SOP deals with JavaScript on one page manipulating another page. So SOP deals with pages interacting with each other. Cookie policy deals with sending cookies across to web servers. All right, now let's talk about CSRF, cross-site request forgery. Okay, so CSRF attacks build right off of the cookie policy that we just talked about. So now we know, based on cookie policy, that browsers will automatically attach stored cookies if they meet the requirements of cookie policy. So what's stopping us from making an evil site that does something like this? It loads an image with the domain bank.com/transfer and then transfers $100 to Mallory. Now, if this is run on a browser and the browser, the user is signed in to bank.com on this browser, this request will be sent across with the session token of bank.com because that is the request that is being made. So your browser will send the session token across and a request will be made to this transfer function on bank.com, and the money will potentially be transferred. So what is stopping us from doing this and making a bunch of evil sites that do this sort of thing? Well, CSRF is what protects against this. So CSRF tokens are these randomly generated tokens that we embed on form fields. So anytime we have sensitive form fields, so maybe we have this transfer form field where we have person and amount on bank.com. Maybe one additional thing that we do is we have this hidden value here that is some random number. And the server knows this random number because the server is what essentially generated this bank.com web page for the browser. So remember, when this web page was generated, there was a GET request, and we got back some, website. And this all came from our server. Now, when we actually make the transfer function, or when we do, /transfer, we will include one additional attribute here, that is this random number. And effectively, what this will say is that this very first time we establish this connection, we put that random token there in this hidden form field, and every future time you want to actually transfer money, we attach this random number, and the server checks to see that that random string matches. And so what this effectively lets us do is to ensure that only this website in this context is allowed to actually make a successful transfer. So if this transfer request originates from evil.com or some other websites, it won't have the random number, and therefore the reject will be requested by the server. So that is CSRF tokens in a nutshell. And the other defense against CSRF is refer validation, where each website has a refer that is sent along with every HTTP request. And so in this case, the refer is bank.com. And in the case above, the refer is evil.com. And so the refer is something that is attached by the browser. And so if you're using something like Safari, Safari will attach this refer to every HTTP request that is sent across. And your server can check to see that the refer is coming from the right place. So we want to make sure that the refer is bank.com in this case here. But note that some privacy tools and some browsers strip all outgoing refer headers for privacy reasons. And so refer validation is an imperfect system. It does not always work. And so CSRF tokens are typically the way to go here, but often websites will include both of these defenses for extra protection. So that is it for this mini lecture. And this is a summary of all of the different topics that we've covered so far. We have same origin policy, cookie policy, CSRF attacks, cross-site scripting or XSS, and SQL injection attacks. All right, now let's move on to the discussion worksheet. All right, Now we're going to take a look at the discussion worksheet for this week. So question 1, session fixation. So a session cookie is used by most websites in order to manage user logins. So this talks about session cookies in general. So the server sends a randomly generated session cookie to the user's browser, and the server stores the cookie value in a database along with the corresponding username. The user's browser sends the session cookie to the server whenever the user loads any page in the site. The server then checks the session cookie up in the database and returns the corresponding username. Using this, the server knows which user is logged in. So some web application frameworks let cookies to be set by the URL. So visiting this sort of URL, where we have session ID equals 42, will result in the server setting the session ID cookie to the value 42. So can we spot an attack on this scheme? Well, the attack in this case is effectively known as session fixation. And how this works is, say we are potentially on a bill paying website or something like that. So say we have this website where we sign in and we can pay our bills. And say our session ID token is 42. So if we want some other person, say Alice, to pay our bills for us, what we can do is send her a page and set the session cookie value in the URL as a URL parameter. So if we send her billpay.com/pay, and then we say session ID equals 42, this will effectively sign her in as us by setting the session cookie value to our session cookie. And so when she goes and maybe puts her credit card information in and signs in, her browser will treat this as being signed into our account, and she might go through and pay our bills for us. And so this effectively lets other users, so attackers, this lets attackers fix the sessions on their victims' browsers, and that is potentially dangerous in that the attacker can get the user to do things that they shouldn't be doing under a different account. And so in general, we don't want these session cookies to be set by things like URLs. We want these to be only set by the server in the response to an actual GET request. So when we have a browser and our server, right here in this request, that's where we want to set the cookie. And because when we do it like this, the attacker doesn't have control over what this cookie value is. And so compared to this structure here where we're setting the session cookie in the URL, this more common structure makes sure that only the server is capable of setting the actual value of the cookie. And so that is typically more secure. Part B says that suppose the problem you have spotted has been fixed. foobar.edu now establishes new sessions with session IDs based on a hash of the tuple username and time of connection. Is this secure? If not, what would be a better approach? So in general, let's see, we have a username and a time of connection. This is actually less secure. So this doesn't directly address the issue that we had above of, this vulnerable setting the session ID in the URL. So that's the first concern. Doesn't address issue above. That's essentially like a fundamentally different problem. And second thing is, just in general, we are effectively weakening the entropy of the session cookie. So because we have a username, which is somewhat known, and a time of connection, which is also potentially something that's guessable, our session cookies are not very secure because they don't really have that much entropy. So we've reduced entropy of session cookie, which is bad, because now an attacker might be able to guess that actual session cookie value. And so the secure way of doing this is to make sure that the session cookie is randomly generated. And we want to use this architecture above here. So we want to make sure we send it back through the HTTP GET and POST requests, not setting. We don't want to set these values through the URL itself. All right, so that is question number 1. Question number 2, cross-site request forgery. So in a CSRF attack, a malicious user is able to take action on behalf of the victim. So consider this example. Mallory posts this comment in some chat forum. And what does it do? Well, it has an image source, and so this URL is effectively loaded as soon as this chat page is loaded. And what does the URL actually do? Well, it has patsybank.com/transfer amount 1,000 to Mallory. So in this case, Mallory is getting other people to transfer money to herself. So, of course, Patsy Bank won't let anybody request a transaction on behalf of any given account name. Users first need to authenticate with a password. However, once a user authenticates, we have their session ID being associated with a state. So we are essentially using session management here, where we have some sort of session cookie that's stored in the browser, and every time we make requests, we're sending that session cookie across to the server. So part A asks, explain what could happen when Alice visits the chat forum and views Mallory's comment. So in this case, if Alice is signed in to Patsy Bank, then the browser will attach any session cookies that are saved by Patsy Bank when this URL is loaded, when the GET request is made. So if Alice is signed in, $1,000 could be transferred to Mallory. And that's because this is just a GET request to this URL. That's made as soon as the page loads and this image loads itself. And so this GET request is made and the browser attaches cookies. And one of the cookies is the session token cookie. And that session token cookie is for Patsy Bank. Now, if Alice isn't signed in, then her session token cookie won't really exist because she hasn't established a session with Patsy Bank yet. And so if she's not signed in, then nothing really will happen here. Okay, part 2 is asking, Patsy Bank decides to check that the referrer header contains patsybank.com. Will the attack above work? Why or why not? So in this case, the referrer header will be some sort of chat application. So let's just say like chat.com. And so when this image is loaded, the referrer will be chat.com. Okay, so Patsy Bank, when it receives this GET request, it will check to see that the refer is Patsy Bank, or it contains patsybank.com. Because in this case we just have chat.com, the attack will fail. So no, because referrers will not match. So if Mallory wants to modify this attack to get around the check, one thing that she can do is load this URL through a dummy website. So maybe we have control over chats.com / patsybank.com / other / something else. Okay, so say we control this sort of URL or something like this. If a request originates from this page, and that goes to our server, then effectively what's going to happen is the server will check to see that the refer header contains patsybank.com. And because we have our refer header, remember our refer is this whole thing, and it will contain patsybank.com, and because it does contain that, we will get past this simple check here. Okay, part D is asking, recall that the refer header provides the full URL. HTTP additionally offers an origin header, which acts the same as the refer header, but only includes the website domain, not the entire URL. Why might the origin header be preferred? So the origin header, because it only contains this chat.com and doesn't include any of this other information here, it is effectively providing privacy. So if you have something that looks like our link above, where we had Patsy Bank and this whole URL up here, bring that down here. This URL has a lot of information in it. It has this domain here, and it also has a bunch of data in the path. So it has the amount and who we're transferring to. And in general, if this information is being sent to a website, say, it's being sent somewhere, the refer will include all of this information. So say we are on patsybank.com and we're loading an image from, a different web server. So we're loading an image from Google. If we're on Patsy Bank, we don't want to tell Google when we load this image that, Mallory is transferring $1,000. We will only want to tell them that this request is coming from patsybank.com. We don't want to give them any of the other information that might be in this path. So effectively, if we just use the URL origin, we protect the privacy of our users by effectively hiding any other information that might be stored in the path whenever we make requests to other websites. Now, part E is asking, assume all browsers support an additional cookie field, same site. When same site equals strict, the browser will only send the cookie if the requested domain and origin domain correspond to the cookie's domain. Which CSRF attacks will this stop? Which won't it stop? Give one big drawback of setting same site equals strict. So this, in practice, will stop most CSRF attacks, almost all of them, in fact. But in the case where we have some sort of other vulnerability, so perhaps an XSS, if we have other vulnerabilities such as XSS, then those might allow us to bypass CSRF validation. And we'll take a specific example of this down at the bottom. Now, one of the big drawbacks of this is that when we have some sort of same-site strict validation turned on, if we're on a website like gmail.com and we click on a link to Facebook inside of this, when we go to Facebook, the browser will make a request to facebook.com from the source of Gmail, from the origin of Gmail. And because it's coming from the Gmail origin, it won't contain the cookies for facebook.com. So if you're signed in to Facebook and the request is originating from Gmail and you have same-site equals strict enabled, cookies will not be sent. And the user will have to log in once again. And so this significantly limits functionality because we'll have to keep signing in to these sites if we click on links in other web pages, embedded on other web pages. All right, that is question number 2. Now let's move on to question number 3. CSRF++. Patsy Bank has learned about the CSRF flaw on the site described above. They hired a security consultant who fixed it by adding a random CSRF token to the sensitive transfer request. So now we have this token field here, and this token is chosen randomly and it's separate for each user. So now Mallory starts looking at the welcome page and she loads this sort of URL in her browser. And what is this URL? Well, it has a script alert script in it. So this is an XSS attack, specifically reflected XSS. And we can tell that because we have some JavaScript that's embedded inside of a link. And so that is indication of reflected XSS. And the way to verify that is that when the page is loaded, Mallory saw an alert that said jackpot. And so what did we see here? We saw a JavaScript alert. And because we saw it pop up, that XSS was successful. All right, so now part A asks, what kind of attack is the welcome page vulnerable to? Well, we just talked about it. This is reflected XSS. And one note here is that these are usually found anywhere the user is inputting some data and that data is getting rendered on the page. And so search pages are really common sources of this attack. Okay, now part B asks, Mallory plans to use this vulnerability to bypass CSRF token defense. She'll replace the alert jackpot with some carefully chosen JavaScript. What should that JavaScript do? So in this case, the big idea is that we want a way to get access to this token here, this random token that's generated. So what we do is we first load a payment form. Then we extract that token. And then we can make arbitrary requests. We can make a transfer request with that token. And so in this case, we are running in the context of being signed in as whatever user this is. So let's just say Alice. And when we load this payment form, we get a CSRF token. And when we make that request, we can just attach that token and perform whatever actions we would like on patsybank.com. And we know the token will match because we stole it straight from the form. And if the site has any cookies, those cookies will be attached as well. And so this sort of bypasses CSRF token defense. All right, part C is asking, does same site equals strict stop the attack from part B? Well, no, not really, because same site equals strict only applies when your site is different. And so in this case, because all of these requests here are originating from the same site, patsybank.com, same site equals strict doesn't do anything. So no, because requests originate from patsybank. Right, and part D is asking, Mallory wants to attack Bob. Name one way that Mallory could try to get Bob to click on a link she constructed. So this is a super high-level question because there are many, many ways of getting people to click on links. So I guess the most common is to just send an email with that link and do some sort of email phishing attack. And so that is it for this discussion.